Alright, welcome back to week 2 of trying to land a model rocket without using a parachute. Crazy, right? Last week I described how I would go about using the thrust vectoring system, and it's still in development, all the 3D printing and stuff. I managed to be able to get it to 3.6 inches in diameter, the whole thrust vectoring mount. However, you can't really buy 3.6 inch airframes. I would have to buy like a 3.5, and I'll just try shorten up the thrust vectoring mount so it could actually fit inside the 3.5 instead of have to somehow expand the cardboard up to 3.6. I don't know, that sounds complicated, so I'm just gonna do it all in CAD. Also, I put that project a little bit on hold because it took me a while to get these bad boys, these linkage stoppers. They're really good for like RC planes and stuff, like where you'd have a servo motor controlling this, and it would kind of like pull this in and out, or like rotate something, for example wings or something. However, I'm not using it on an RC plane. I'm putting this on my thrust vectoring mount. Like the servo motors will control that. So that whole thing was on hold because I needed to get these parts, and here we are. Hopefully I'll have it done by week 3. And also, I put in another order with that to get this Teensy 3.6. It reduces complexity as compared to my old Arduino Uno, because for one, I don't have to have a SD card module installed on this, and secondly, I'm no longer bottlenecking at the amount of computer processing power on this. So the CPU on this clocks in about 128 megahertz, while the Uno significantly less than that. I forgot the number off the top of my head, but this is I'm not going to bottleneck at this, I'm sure that. Plus you can overclock these, which I thought was a pretty interesting feature. You can go up to 256. That's overkill at that point. I'm not too concerned with that. I'm just going to use it as is, not try to damage the CPU or anything. So really the only bottlenecks that I have are trying to get data to travel on the I2C protocol on the serial clock lines. This week I am going to be focusing a lot more on telemetry and the user interface for my rockets. So alongside with the Teensy 3.6 that I've started to interface with, and this OLED module that I'm going to put on the side of my rocket, I've built this, oh gosh, it's falling apart. I built this transmitter / receiver. Like, you'll be able to transmit data such as like deploying a parachute just in case of emergency, or maybe possibly igniting, but like instead of having an E-match, you could just use this. You'd still have an E-match, but it would be located on the rocket instead of like the traditional, like you just press a button, signal goes through and just burns an E-match. You could do it like remotely. You could check the status of the rocket from here. So lots of implications I could use this for, hundreds even, but I'm probably only going to use like the 3. Either status update, ignite the motors, or check for location. I'll go into detail about that later, but this week will be a little bit more focused on the user interface and graphics processing and stuff, using different displays. So I'll be able to interface with the rocket a lot better. Like, troubleshooting might be easier. Like, I would be able to just check from this instead of having to bring my laptop around everywhere. So I'm still gonna bring my laptop to like test launches and stuff, but it would just be nicer to have like a little display that says this is currently working, this is not, this is. GPS is online, IMU is working, pressure sensor has not been updated, and it goes through a sequence of updates or something along those lines. So I figured it would be easier to take a step back and start working with the interface, so everything would be able to fall into play a lot easier if I'm able to see what's happening inside my inside my processors, inside the rocket, inside my telemetry and all that. Alright, so here's my jerry rig of a receiver. Currently it's running off of 9 volts. I might change that. I could use one of those LiPo rechargeable ones that I have, but this will get the job done for now. As soon as I plug that in, it actually turns on. There's a booting sequence that you probably missed because it fell over, but boots up, and then everything falls apart because everything is not soldered in correctly. I haven't soldered anything down because nothing's final. This is all just kind of like just slapped together just so I could have something that works and functions accordingly before I have anything set in stone. Like eventually have all of this like 3D printed inside of a casing. But it asked me if I want to press a button to continue, and I'll press a button. I can view the menu, like I could view the status of the rocket. This is what I was talking about earlier. I can troubleshoot probably from this. It might be easier from the computer, but it's always nice to have like as it's on the launch pad, I could see like what's online and not or not. It appears that the camera is not at the same rate as. Actually, I don't know how it's working, but it's flashing in real life. I'll tell you that. You probably can't really tell from the screen on my phone, but I can move around. I can actually start the ignition from this. Like I would be able to send a message that, say, turned a transistor on that allowed like 9 volts to flow through a match head and ignite a motor, or I could use like start ignition as like, say, start ignition inside of ejection charge that shoots a parachute out in case like recovery goes wrong. I just like override it by using this. And finally, another setting that I have, like location update. I could track the position of the rocket via GPS because I'm going to have a GPS on board. So yeah, I could have a multitude of functions. Say when I select location update, returns the latitude and longitude. Don't have that working right now because the NRF, this freaking this receiver right here, has been giving me quite the struggles recently, but I hope to get that working soon. In addition to the telemetry side of my rocket, I've also been working on the theoretical height that I have to be at in order for the amount of energy dissipated from the rocket engine in order to counteract the amount of kinetic energy as the rocket's falling. So what this means is like the rocket is at a certain height, it falls and it speeds up, right? As it falls down, it loses gravitational potential and converts into kinetic energy. As it falls, it speeds up. So at one of these points, it's at a specific velocity to where all of that energy can cancel out as the rocket engine is pushing up on it as soon as it ignites. So all of the kinetic energy, say here, it's traveling really fast, can be dissipated by a rocket engine pushing up, and like this energy is about the same as this energy, and they both kind of counteract at the very end of its burn, and it results in no kinetic energy as well as all the energy dissipated from the rocket engine. So in order to derive an expression for the amount of energy stored in the rocket propellant, we can rearrange some physics equations. For example, impulse is equal to the force times the amount of time it's burning, the engine's burning. So typically your motor manufacturer will give you the amount of impulse. So we're going to use that as a baseline to figure out the amount of energy stored. So since impulse equals force times time, we can rearrange that, figure out force equals impulse divided by time. So energy is also force acted over distance. We just found the amount of force that the rocket can give off. So the amount of energy stored in would be the impulse divided by time times the distance it's acted over. So really, it would be the impulse times the velocity of the rocket would be the amount of energy, the kinetic energy stored. So, sorry, not the kinetic energy. It would be the amount of just the energy, like the chemical potential energy stored inside the rocket. And we want this to be equal to the amount of kinetic energy because, remember, as it's falling, it gains energy, and we want eventually, at a certain speed, we want to be able to cancel all that speed out with the amount of chemical potential energy stored in the rocket. So we want to hit exactly that when we ignite, but in terms of physics, we will just set these two equal to each other. So we'll have 1/2 mv squared kinetic energy equal to impulse divided by time times distance, or the amount of chemical potential. So when we solve for the amount of velocity, we end up getting 2 times the impulse divided by the mass. So we just divide out the velocities and rearrange the equation to solve for v, and that would be the speed at which you would have to ignite the motor to cancel out all of that energy. So the speed is 2 times the impulse divided by the mass of the rocket, which it makes sense. So like if you have a really huge mass, that means the denominator would be really big, so that means you have a really small number in general. So that means your velocity would have to be really you'd have to have a really slow velocity in order to stop a huge mass. Like, it would have to be, it kind of makes sense, like a really big chunky guy running at you, you would have to be moving really slow to be able to stop him with like my tiny scrawny arms. And then on the other hand, if you had a huge impulse in the numerator, that means you would have a lot of energy stored in your rocket. So that means your velocity could also be really big. You could be traveling super fast, but since you have a really huge impulse, you're able to counteract it. And now, to figure out the height from when you ignite to where you dropped off from, we can figure out the amount of kinetic energy that was derived from the gravitational potential energy. So eventually, if you were this high and you fell, all that energy from the majority of all that energy from gravitational potential energy equals kinetic energy, and all that kinetic energy was dissipated by the rocket. So we can use 1/2 mv squared kinetic energy equal to the amount of gravitational potential energy, or mgh, to find when the two equal each other, basically. And we end up dividing both sides by mass, and then you end up with 1/2 v squared equals gh, which is essentially like the accelerations of both are equal to each other. And we just figured out the velocity at which you would have to ignite the motor. So we can plug that back into our original equation and then solve for h, solve for that change in height from when you're falling to when you ignite. So h turns out to be 2 times the impulse squared divided by your weight squared divided by the acceleration due to gravity. So with the motor that I'm going to be using, hopefully gives an impulse of about 80 newton seconds. And if you were to plug in the amount of acceleration due to gravity, the 80 newton seconds of impulse, and then multiply by 2 on your left side of your equation, you could solve everything in terms of just h and m squared. So you end up simplifying to about 1,306 divided by your weight squared in kilograms equals the height that you're allowed to drop from. So here we have one of my favorite online graphing calculator programs. It's called Desmos.com. It's pretty good for graphing whenever you need it, I guess. Here's me graphing 1,306 divided by the mass squared equals h. So that's my function right there. That would tell me y is how high I'm allowed to drop it from when it's like drops from a drone or a rocket to when it ignites. And that x in the denominator is the weight of the rocket. So like as weight increases, I have lower, like as my weight increases to like 56 kilograms, I would never get to this big, but you can tell that it makes sense. Like you get a huge mass, you're not allowed to drop it from that high. Matter of fact, I would only be able to drop it from 0.3 meters if I were to get all that impulse to burn, which probably wouldn't happen. It's in the span of 8 seconds, it wouldn't be able to pick up 60 kilograms in like that short amount of distance. On the other hand, if I had a really tiny mass, like say for example, not negative mass, but like let's say 2.2, because that's the restriction on flying with, I think, like level 0 certification. So 2.2 would be right around, let's just say it's right here. I would be able to drop it from about 260, maybe 265 meters up, which is pretty significant height. I probably would not be dropping my rocket from that high, but this program just goes to show that I can use a fairly simple algebraic expression to figure out how high I'm allowed to drop it, or give me a rough estimate to where I can start actually developing systems and figuring out weights and what my weight restrictions are. So it seems to me that like I could get to about 5.5 kilograms of weight and still be at a pretty reasonable height to test this system. 44 meters up is pretty high, so I think I'd be able to test this system even at 44 meters high and 5.5 kilograms. So I don't think weight would be too much of a restriction right now. Maybe I did the math completely wrong, and you know that's highly likely. But this will just go to show to see if we can test this and see if our results stick up with this. Hopefully I can, when my first test happens, I'll be able to drop it from, say, 262 meters, which is pretty crazy, maybe from somebody else's rocket, as it like gets to their apogee and it comes out, it lands itself from gaining all that kinetic energy. But then again, you also have, say for existence, energy dissipated from air resistance. So that would also come into play. That would probably lower the amount of height I'm allowed to, the height from my apogee towards my ignition point. So if I include air resistance, I would probably have to account for a much larger, say, height. My height would decrease. Alright, so that's all for this week. Week 2 has been a little bit procrastinated because I was supposed to have an upload about a couple days ago, but my goodness, calculus has been kicking my butt. But I feel like I've made pretty decent progress for this week. Got some actual stuff in the making, actual physical models that I can actually hold in my hand, which is pretty nice. I'm just going to keep doing this, just eventually 3D print everything and hopefully have even more solid models that I can work with, and then eventually have a rocket done by December. That's the goal. I'm going to keep looking for it. I'm going to keep saying that every week, maybe. And I've got a couple people working on this with me, Harrison and Aaron. So we'll see how that turns out. I bet there'll be lots of help, especially since they have experience in CAD and stuff, so we'll be able to all work together and hopefully even do uploads together maybe. I'm looking forward to this. I'm looking forward to working with people and actually understanding this whole engineering idea. Right, well, thank you, and I'll see you next week, hopefully.